So we were here last time. Yeah. So we just found the solution. Finding the minimum, we need to use n-1 comparisons to find a solution. Yeah. The question is it the best solution? Is it possible that someone can do better job, can find the solution in n-2 comparisons? If that is possible or not. So we want to look at this question. Just to improve our current solution by one comparison, if that is possible. That's what we are at this point. That is the optimality problem. The question is if our current solution is optimal or not. Okay? Yeah. All right. So let's continue this discussion. Yeah. Is it possible to further improve the algorithm? Yeah. So every time when we find a solution, after we find a solution, we want to consider this question. Yeah. Is it possible to further improve the algorithm? Yeah. So usually there are two directions we can go. The first direction, we try our best to improve the algorithm. The first option. The second option, because the first option, if you try very hard, you may not be able to do it, right? No matter how hard you try, you couldn't do it, okay? Yeah. Then you may think about the second option. Yeah, because you may not be able to improve your solution because your solution is already optimal. Okay? Yeah. If your solution is already optimal, you need to convince people that it is already optimal. Okay? You need to make rigorous arguments to convince people it is already optimal. Yeah. All right. So here, let's try this optimality discussion. First, we want to improve, but think about, so we want to look at our options, and we feel we have no idea how to improve our current algorithm. Yeah. So we cannot see any special way we can use to improve our current algorithm. So now we want to look at the second option. Is the current solution already optimal? Yeah, it's possible. Yeah. But we need to make convincing arguments. All right, so let's look at post-solution thinking. Yeah. We should try to improve the solution as much as we can. Yeah. That's our first option. Okay, so you want to try something first. But you may fail, so then you consider second option. Yeah. All right. Yeah, but here, in order to show people your current solution is already optimal, usually it's not easy. Yeah. So here, this simple question. So look at our problem number 3. It is quite simple, right? Even for the simple computing problem, if we want to show it is optimal, our current solution is optimal, still it's not that easy. Yeah. Why it is not easy? What's the meaning? What do you mean it is optimal? What do you mean it is optimal? First, we need to understand the meaning of the optimality. What's the meaning? It is optimal, that means our current solution is the best. Nobody can improve it, right? So nobody can improve it. Not just us. Nobody in the world can improve it, right? Nobody in the world. Not just us. If someone in some small island can improve, we cannot say it's optimal, right? Yeah. So nobody in the whole world or nobody in the universe can improve it. Let's say it this way. Nobody in the universe can improve it. Then we can say it's optimal, right? Yeah. Otherwise, someone in a different planet can improve. Then we cannot say optimal, right? Yeah. So nobody in the universe can improve it. Okay? All right. Then there is another issue. Even nobody in the universe can improve it. Can we say it's optimal? Even, let's assume nobody in the universe can improve it. Can you comfortably say it's optimal? You can say, yeah. Try to think a little more. Yeah. Currently, let me use this word. Currently, nobody in the universe can improve it. Can you say it's optimal? No. Because after 2,000 years, someone can improve it. Then we cannot say optimal, right? Yeah. So when you say optimal, even after any number of years, still nobody can improve it. Then we can say optimal, right? So it must be absolutely optimal, okay? It must be absolutely optimal, then you can say it's optimal. Yeah. So that's why I say it's not easy to prove it, right? Yeah, all right. But the question, is it possible? Yeah. You may feel it's impossible, right? How to make that convincing arguments, right? So, yeah, even because you cannot predict future, right? How can you predict future? Yeah, someone extremely smart can improve it. Yeah, all right. So the hard part is we need to consider all the possible algorithms solving this problem. Can you imagine how many algorithms, how many possible algorithms that can be used to solve this problem? Can you imagine that? How many possible algorithms? Nobody can imagine that, right? Nobody can imagine. So think about, is it possible to exhaust all the possible algorithms that can be used to solve this problem? Nobody can exhaust, right? All right. So if nobody can exhaust, there are many unknown algorithms. We don't know. There are so many algorithms out there solving this question, but we do not know. We do not know those algorithms. How can we say our current one beats every other algorithm, no matter what? Okay? Yeah. No matter what. Our current algorithm, at least not worse than that algorithm. Yeah. At least as good as that one. Never worse than any other algorithm. How can we say that? Yeah. So this is the hard part. Because there are so many unknown algorithms. The question is, how can we cover unknown algorithms? In our discussion, how can we cover all the unknown algorithms that solve this problem? Is it possible? Is it possible we make discussion to cover all the unknown algorithms? Is it possible? The answer is yes. The answer is yes, it's possible. Okay? Even you don't know, you can cover. Even those algorithms, you know nothing about them. Yeah, actually, you know something. No, you know nothing. You know something. Yeah. Because those algorithms can be used to solve this question. That's what you know about those algorithms. Okay? Other details you don't know, but this aspect you know. That algorithm can be used to solve this particular question. Yeah. All right, question. How do you study unknown algorithms? Here we want to study unknown algorithms. If you want to cover, you need to study unknown algorithms. Is it possible to study unknown algorithms? Yes. Yes, it's possible. Yeah. Let me tell you how to study unknown algorithms. Okay? Yeah. Here, we're going to do that. Yeah. Next slide, we will do that. We will study unknown algorithms. All right? Yeah. Yeah. So the answer is yes, it's possible to study unknown algorithms. How? How to do it? Yeah. So let me give you the answer, how to do it. How to study unknown algorithms. The answer is discover some common property or properties for all those algorithms. Common property. If we can discover some unknown property or properties covering all the unknown algorithms that can be used to solve this particular question, then we can use this property to study those unknown algorithms. That's the answer. Think about that. But the question, how do you discover common property, right? Yeah. It's hard, it's not easy. Yeah. But it's doable. The question is, it is doable to discover some to discover some common property for those unknown algorithms. Yeah. So let me show you the next slide. We will discover some common property or properties. Okay, several properties. Okay, properties. All right. Let's do the discussion. How we convince people that the algorithm is optimal. Yeah. Okay. So here, we need to use our real world experience in our arguments. So we need to use something, some special situation that we can understand better. So we want to understand our current situation better. So here we borrow some real world similar situation to help us understand our current problem solution. Yeah. So what's that? Recall your experience in playing sports game. Playing sports game. So you're familiar with, general sports game. Okay? Yeah. So here, let's talk about general sports game. Let's imagine two players. They play each other. Yeah. So one player wants to beat the other one. That situation. Okay? So we use this special activity to understand a comparison. Here, what we are doing, we want to do comparison, right? We compare the values of two elements. Which one is larger, which one is smaller? Yeah. Is this similar to the situation that two players in a sports game play each other? One player wants to beat another one. Similar, we want to use that. We are familiar with that. So we can, try to understand. Yeah. So the comparison, so we use a match in a sports game between two players. Yeah. Usually the results, yeah. Because here our goal is finding the minimum. Finding the minimum, that means the smaller the better. Right? The smaller the better. So not the larger the better. Okay? Eventually, the smallest one is the final winner, right? The smallest one is the final winner. Yeah. So that means here we need to adjust our criteria. Okay. The smaller the value, the better we want to pick. Okay. So that it, in that aspect, we'll set that one as the winner. Okay, the winner of the two players, the one with smaller value is the winner. All right, yeah. Equal, tie. Okay, yeah. All right, greater than. Yeah. If the value is greater, yeah, in this particular question, yeah, lose the game. Okay, yeah. All right, yeah. But there is a important difference between our comparison and playing sports game. That's it. Although it looks similar, but in a very important property, it's different. These two things are different in a very important property. What's that? When we do comparisons, we follow transitivity property in arithmetic, right? Transitivity, you know transitivity property, right? Transitivity, what's the transitivity property? Yeah. So if PA greater than PB, okay, player A is greater than player B, okay? PA, yeah, here, variables. PA variable is greater than PB variable. And PB variable is greater than PC variable. By transitivity, we can conclude PA value is greater than PC value. That's the transitivity property. Okay? But in our usual sports games, we don't have this property. So we never have this property, right? Player A beats player B, player B beats player C. We cannot assume player A beats player C, right? Yeah. It's possible player C can beat player A, right? Yeah. Yeah. It happens all the time. Okay? It happens all the time. Yeah. So in sports games, we don't have the transitivity property. But here we need to use it, because in our comparison, we have this property. And this property plays a very important role. So we cannot skip, we cannot ignore this important property. Yeah. So we need to apply it. Yeah. All right. Yeah. So when we apply it, you will see we have a different concept when we compare the values of all those elements. We have a different property. Okay? Yeah. So let's see. Yeah. Here, because when we apply the transitivity property, yeah, so we have a special situation that we can compare two elements indirectly. We can compare two elements indirectly, not directly, indirectly. So we do not really compare A and C. We just, after we compare A and B, if A greater than B, and compare B and C, and we know, if we know B greater than C, then we do not need to compare A and C explicitly, right? Because we already know A is greater than C. So we call this situation as A beats C indirectly. A beats C through transitivity. A beats C without doing direct comparison. How about that? A beats C without doing direct comparison. A beats C through transitivity. Okay, so we have this situation. So we will use in our discussion. All right. After you understand all these things, now we can do the convincing arguments. Try to convince people. Yeah. Try to convince people it's optimal. Okay? Yeah. Next, let me show you the convincing argument. Step by step. Each step, make sure the statement must be completely correct. Then we can move to the next statement. Okay? Make sure every step, the statement must be correct. Yeah. Then we can move on. Yeah. All right, let's look at a convincing argument. The first one, yeah. Imagine that min is the final winner. Yeah. So we set up. Yeah. So we're looking for the final winner. So that's the minimum element in the whole array, final winner. Yeah. So that's our goal. We are looking for the final winner. Yeah. All right. Next statement. It needs to beat, this final winner needs to beat all the other elements in the array through comparisons. But two types of comparisons, direct comparison or indirect comparison. Here we need to add the indirect comparison. We feel it's legal to use indirect comparison. Okay? So what's the indirect comparison? Comparison through transitivity. That's the indirect comparison. Transitivity property. Okay? Yeah, that's legal. Yeah. So we can use indirect comparison. Okay? All right. Yeah, so this statement should be okay, right? No problem. Yeah. Next statement. If an element loses once, it is eliminated. If in one of the comparisons, one element is lost to another element, then it's gone, right? Then that element cannot be the final winner, right? If one element loses once, it cannot be the final winner. If it cannot be the final winner, we can comfortably eliminate it from our consideration, right? Yeah. Because our goal finding the final winner. Yeah. Yeah. So here, if one element loses just once, yeah, then it's gone forever. Okay? So that's no problem. This statement. Yeah. Correct. Completely correct. Right? Yeah. Then move to next statement. Each comparison can only eliminate one element. Oh, can only eliminate at the most one element. How about that? So if I want to say precisely, can only eliminate at the most one element. Let's understand this statement, correct or not. First, is it possible that one comparison eliminate two elements? Is it possible? Yeah. Think about two players. They fight each other. After they play, both players are eliminated. Is it possible in our sports game? No, never, right? Otherwise, why you fight? If you're both already eliminated, you both are gone, right? Why you fight? Why you play? It's unnecessary play, right? Yeah. So, if before the game, yeah. So we don't know. So let's assume, yeah. If a player already eliminated, so we do not need to play. If our goal is the final winner, we only want to pick the champion. Okay. We do not need to rank other, people, other players. Okay, yeah. Then, if one player is already eliminated, then that player does not need to play useless games, right? Yeah. Here, think about in that situation, it's impossible that two players. Before the game, we don't know. Before the games, they are not eliminated. They are both qualified to be the final winner. Let's say this way. Before the game, both players, they are qualified to be the final winner. And after the game, they both eliminated. Is it possible? It's impossible, right? You can only eliminate one of the two. You cannot eliminate both, right? Yeah. But here, I put at the most. Yeah, actually, I can safely remove at the most. Yeah. If we made this assumption, we can remove at most. If we say, before the game, two players are qualified for the final winner, then we can eliminate at the most. Yeah. Because we don't want any player without any chance to be the final winner involved in the games, right? Yeah. Yeah. We want to save our resource. Okay? Yeah. All right. So with that assumption, then we can remove at the most. Yeah. So then we can say this way. Each comparison can only eliminate one element. Okay? Yeah. So now this statement is correct, right? Yeah. Correct. Okay. Yeah. All right. Then, yeah, so here I say at the most, yeah, because at this time I do not assume, yeah, because when I say at the most, because one of the player already lost the chance to be the final winner, but the other one still has the chance. One of the two, one has no chance, but the other one still has the chance. Yeah. But if we do not, we change our assumption. If one player has no chance, it's gone. Yeah. It's gone. Yeah. If we change that way, then we do not need to consider this case. Okay? We do not need to consider this at the most case. Yeah. Okay? Yeah. All right. Next step. Yeah. Now the final statement to complete our arguments. Okay? Yeah. Because now let's look at our final step. Yeah. Our final step is, in order to get a final winner, we need to eliminate n-1 elements, right? You have to eliminate n-1 elements. Then only one element survives. That one is the final winner, right? Yeah. So after you do certain number of comparisons, then n-1 of them must be eliminated. How many comparisons can eliminate n-1 elements? One comparison can only eliminate one. You need to eliminate n-1, so you need n-1 comparisons. Think about that. One comparison, you can only eliminate one. But we know at the end, we need to eliminate n-1 elements. You cannot use fewer than n-1 comparisons, right? If you use fewer than n-1 comparisons, then you can only eliminate fewer than n-1 elements. Not done yet. You need to eliminate more. So in order to eliminate n-1 comparisons, so we need at least n-1 comparisons. Here we say at least, because some people may do some redundant comparisons, right? Yeah. Some algorithm may do redundant comparisons. If they do redundant comparisons, they use more than n-1 comparisons. Okay? Yeah. Yeah. But the minimum is n-1 comparisons. Can you see that? The minimum is n-1 comparisons. Okay? Yeah. So nobody can use fewer than n-1 comparisons to find the final winner. Yeah. Look at that argument. Okay? All right. Yeah. So after that, then our conclusion, this algorithm is optimal. No. That's the, we treat very rigorous. So our arguments here, very rigorous. No hole. Okay? Yeah. Every statement must be correct. Okay? So then the whole proof is correct. Okay? Yeah. So after this point, then you can use the conclusion directly. Yeah. So this algorithm is optimal. Okay? Yeah. All right. So any question? Yeah. Here, although this question is so simple, later you will see this question, the result of this question is so useful. Later, in our homework questions, in our test questions, you will see the result will be used multiple times. And you may not be able to aware of it. Yeah, at least 5 times. Okay. Later in our homework and the tests, this result will appear at least 5 times. Yeah. Yeah. But you may not be aware of. Yeah. The hard part is you may not be aware of. You can use this result to solve some questions. Okay. Yeah. So this is a very important one. Yeah. It's simple, but very important. Yeah. All right. Next, D.2. Let's apply the result of this question to solve another problem. So this one, finding both maximum and minimum. Yeah. So we need to design an algorithm. Given the array, after we apply our algorithm, we can find both maximum and minimum. Yeah. So we need both. Yeah. So not just one. Okay, we need both. Yeah. Yeah. So let's solve this problem. Yeah. All right. So before we start our discussion, can you try to apply our previous result to solve this one? Yeah. There are n elements. So when you start work on n element array, yeah, here you need to find both maximum and both minimum. Okay. Yeah. You can use our previous result to solve it. Do you want to find some simple, fast way to solve it? Any idea? Simple, fast way, solve it? Yeah. Okay. Straightforward method. First, yeah, because you just apply our previous result in a straightforward way. Can you find the maximum first? Can you find the maximum first? Sure. Yeah. How many comparisons find the maximum? Yes. Yeah. So our first step, finding the maximum, we need n minus 1 comparisons. Okay, all right. After that, after you find the maximum with n minus 1 comparisons, how many more comparisons do you need to find the minimum? N minus 2. Good. Because you already eliminated n minus the max element, right? Yeah. To find n minimum, yeah. So you tell me immediately you need n minus 1. What's the total? The solution, the total, 2n minus 3, right? Yeah. That's how we apply our previous result in a straightforward way. Then we ask our question, is this optimal? No. Every time after we find a solution, we want to think about, is this the best solution we can get? Is there any room for the improvement? Any room for the improvement? Yeah, that's important. Okay? Yeah. All right. Yeah. So here, let me give you some hints here. Yeah. All right. Some hints. Yeah. When you find the maximum, you already put your resource. Here, your resource comparison is your resource, right? Computation resource. So you already invest your precious n minus 1 comparisons, that resource, to get a maximum. Then, in the second round, when you find the minimum, the first round resource you invest, you throw away. You didn't use the resource you invest in the first round. Okay? You start from scratch to find the minimum in the second round. Then there is some probability that you'll waste your resource. You'll waste your resource. You didn't reuse your resource. Remember last time, there is an important point we learned last time. We should reuse our resource. We should not waste our resource. The question, how to reuse the resource here, right? So if you can find a way to reuse your resource, okay, do not throw away valuable comparison intermediate results, then you can save some comparisons. Okay? Yeah. So that's the point. Okay? Yeah. So let's do our discussion. Yeah. You know, try to minimize, you know, wasting our resource. Okay? All right. Yeah. Yeah. Let's consider our data and elements. So I list all of them here. Yeah. Let's review the elimination method we used. Yeah. Yeah. So here in this module, there is a very important problem-solving method. It is called the elimination method. Okay? Yeah. This method in this class we will use many times. Yeah. Yeah. So try to absorb the idea of this important method for this class, elimination method. Idea is so simple, but most of you may not be aware of it. Okay? When you're in a situation applying this elimination method, you may not be aware of it. Okay? Yeah. All right. So when certain elements do not satisfy the criteria, yeah, when certain elements cannot be the maximum, can we eliminate it from the consideration? When certain elements cannot be the minimum, can we eliminate from the consideration? Right? Yeah. Yeah. All right. So we can eliminate them from the consideration. Yeah. Then after the elimination, the data size becomes smaller, right? Yeah. The data size becomes smaller. Okay? You work on fewer number of elements. The fewer, the better, right? For you. Yeah. The fewer number of elements, the less work you need to do, right? Yeah. So that's very natural. Very natural. Okay? Fewer number of elements, then the less work. If you do less work, then you save your resource. Yeah. So that idea. Okay? Yeah. So here, let's use a simple notation in our discussion. Okay? When we do comparison, we use a pair of parentheses. Yeah. Xi, Xj, and a pair of parentheses around them. So denote comparison. Yeah. And put an arrow point to Xi, that means Xi is the winner. Okay, so let's use this simple notation. Xi is the winner. Yeah. All right. Yeah. So then we consider comparisons and look at the winners, losers after certain number of comparisons. Yeah. All right. Winner is determined based on the requirement. So here, yeah, the requirement. Our goal, we want to find both maximum and the minimum. Okay, so that's our goal. Yeah. All right. So details of data manipulation. Here, we move to next step. After we set up our environment, when we start to work, next round, we want to organize our data. Organize our data. Arrange your data in an organized way. Yeah. Based on our experience, we know if we organize in a right way, we can do better. Yeah. we can get a better solution. Yeah. All right. So here there is another important special type of work in problem solving. That is grouping the data. Yeah. When you manipulate the data, you have many different ways to do the grouping, right? Yeah. Put certain number of data elements here, another group containing, certain, some elements with certain property, things like that. Do the grouping. Do the grouping can help you solve the problem efficiently. Later, we will see this grouping idea. So I try to show you how effective can be if you group your data in the right way. So here, the first time I show you, do the right grouping. Okay, all right. So we apply the tournament methods. Tournament in sports games. Tournament, okay? Yeah. So players, so we organize all the players in a tournament, 2 by 2, okay? Every 2 players, they play each other. So the tournament method, okay? Yeah. So the winner move to the next round, okay? The losers are eliminated after the first round, okay? Yeah, that's the tournament method. So that's another commonly used method in our comparison, tournament method. So here we organize the elements using the tournament method, okay? So organize in groups, in pairs, okay? All right, yeah. But there is a question, yeah. Can we get all the elements paired? Because we don't know, we have even number of elements or odd number of elements. We don't know, right? Yeah, sometimes we have even number of elements, sometimes we have odd number of elements. If we have odd number of elements, there is one player left, right? There is a singleton left. Okay. No pair. The first round, that player moves to the next round automatically, okay? Based on our rules in the sports game. Yeah. So here we have the same situation, yeah, but could be different. Yeah. So here, although we borrow that experience, but something could be different. Yeah. All right. So the number of elements, even and odd, when you have 2 cases, here you have 2 cases, even odd case. Okay. Usually, when we have more than 1 cases, there is a simple strategy we use all the time. We work on the simpler case first. When we have more than 1 cases, we always work on the simplest case. Here, which case you feel simpler? Even odd, 2 cases, which one you feel a little simpler? You want to work first? Anyone has an idea? Which one simpler? Even. Yeah. Because even all the players are paired, right? No singleton. Yeah, that's simple. Yeah. So you don't consider the singleton case. Okay? All the players are paired in a perfect way. Okay? So this is simpler. So we want to work on the even case first. After that, then odd case. Yeah. Because when you work on the odd case, you already have the experience and you already have the solution from the even case. Then you can use that, right? You can use the result. For the even case, it could be helpful for the odd case. Yeah. That's the reason we should work on this simpler case first. Okay, all right. Yeah, simplest case. That's the strategy. This strategy we will apply later many times. Very simple. Yeah. All right. Now let's do the work. Okay. Apply elimination method. Apply elimination method. Yeah. So here, let me show you the details of the work here. Yeah. All right. To do it, let's draw diagrams. Yeah. So for this class, because many problems when we compare elements, you may need to do a lot of discussion. Yeah. So here, in order to save a lot of words, usually we use diagrams. Okay? Diagrams to visually represent our ideas. Then we do not need to write a lot of words. Okay? Yeah, so we draw, diagrams. Yeah. So if you convey your meaning, then you do not need to write a lot of words. Yeah. So here, let me show you how to do it. Okay. All right. X1, X2 comparison. When we do comparison, one winner, one loser, right? So here, first, let us assume all the elements are distinct. Yeah. In order to make our discussion simpler, we assume distinct element. Make this assumption, distinct. Don't worry about equal case, okay? Yeah. Then, let's do the comparison. The first pair, X1 and X2 comparison, and one winner, one loser, right? After comparison, you have one winner and one loser. Which one is the winner? Which one is the loser? Either one is possible, right? Yeah, X1 or X2, either one is possible, but we want to make our discussion as simple, as easy as possible. Here, X1 or X2 to be the winner, there is no fundamental difference, right? Because they're symmetric. How about that? If you swap X1, X2, then one becomes the other, right? Yeah. So here, X1 to be the winner or X2 to be the winner, they are in the symmetric situation. Yeah. Yeah. So we can assume X1 is the winner. In this case, we only need to consider one of the two cases. Okay? So here we assume X1 is the winner. Okay? All right. So then, so our discussion, X1, X2, we draw this vertical line segment. X1 on top, X2 at the bottom. Top one means the winner. The bottom one means the loser. Then we draw this simple diagram. Then we do not need to write a lot of words, right? Yeah. So in this way, we represent our ideas graphically, so we can save some words. We can do things faster. Okay? All right. Similarly, next comparison, we assume X3 the winner, X4 the loser, and so on. X5 the winner, X6 the loser, and so on. Okay? Yeah. Keep doing that. The last pair, yeah. Because n is an even number, let us assume n equals 2k. Okay? 2k even number. Okay? Yeah. So here the top one should be x2k minus 1. The bottom one should be 2k. Okay? Yeah. All right. So we arrange n elements. The first round, we do k comparisons. Yeah. So this is the first round. First round. So we do k comparisons. Okay. All right. Yeah. That's the resource you invest. Okay. The first round, you invest, you already spend your precious resource, k comparisons. Okay, so you don't want to waste your resource, right? So you want to, make use of your resource as much as you can. Okay, all right. So our second round comparison. In our second round comparison, we want to do elimination. Now, so here, remember, the main method we used here, elimination method. The question is how to do elimination method. So that's the hard part. So you need to build up experience how to do the elimination method. So here, let me show you this in this example, how to apply the elimination method. Now, you observe the diagram here. I ask you first question. What are those elements that can be eliminated from consideration for the maximum? Right. All the losers, they cannot be considered to be the maximum, right? No losers. Yeah. So you get that quickly. Yeah. Does that mean the losers can all be eliminated to be qualified for the maximum? Yeah. That's a lot of elimination, right? So in this way, you do elimination, half of elements, you can do the elimination. Think about that. Okay? Similarly, what are those elements that cannot be the minimum? What are those elements? They have no chance to be the minimum. No chance to be the minimum. Okay? Easy, right? All the winners, right? All the winners. So here you can see you organize your data in two groups. So I talk about grouping in the previous slide. Here we do the grouping, the right grouping. What's the right grouping? Winners group. This is our first group. Losers group, our second group. This is the right grouping. Okay? When you group your data in this way, in the winners group, minimum is, winners group can never generate the minimum, right? Can never produce the minimum. Losers group can never produce the maximum, right? Yeah. So in order to find the maximum, you only need to do comparisons in the winners group. Okay? So winners group for max. Losers group for minimum. In this way, we can eliminate half of the elements from the consideration. Think about that. That's a lot. Okay? Half of the elements. Okay? All right. Next question. Next question. No. How many comparisons do we need to find the maximum? How many comparisons do we need to find the maximum? What minus 1? What minus 1? N means all elements. N means all elements. K. K minus 1. Okay? K. In winners group, you only have K elements in winners group, right? So for the max from the winners group, K minus 1 comparisons. Okay? Similarly, the minimum, you only do the comparison in the losers group, also K minus 1 comparison. Then total, adding together these three numbers, 3K minus 2, but we need to go back to the N. Yeah, because K, we introduce auxiliary variable. K is not the original variable, it's auxiliary variable. Okay? So we should go back to the original variable N. So that is 3N over 2 minus 2. Here N is an even number, so we know. So this formula must be an integer. Must be an integer. Okay? Yeah. So here you can see. So we find the solution. The solution, if you compare, do you still remember our previous solution? 2n minus 3. Can you compare which one is better? 2n minus 3. Okay? When you do comparisons, here, let me recall, we use approximation method before. We frequently do approximation. When we compare, we can use approximation way. Okay, what's the approximation way? You cross out, you throw away the minor term. Okay, -2, -3, too small. Okay, compare it with n, too small. You can comfortably throw them away. So you compare 2n and 3/2 n. You know what's the difference, right? Half n difference. Think about that. Half n over 2, half n difference. That's a lot, right? Yeah. When n is large, you save a lot of comparisons. You save a lot of comparisons. Okay? Yeah. So this method. Think about it. Yeah. Pretty smart, right? Think about the solution. How much we learn from this example. Okay? Yeah. So the next question is this solution optimal or not? Is there further room for the improvement? Is there further room for improvement? Okay? We need to look at optimality. Optimality of this solution. Now, the optimality of this discussion of this question, very hard. So here I tell you the answer. It is optimal. Okay? The solution it is optimal. Okay? Yeah. Okay? Yeah. For those who are interested in this optimality discussion, so I can create a supplementary video, okay, to show you the very smart way to convince people it is optimal. Yeah. So usually, to convince people a solution is optimal, usually very hard. You need to really find a very smart way to do it. Yeah. So I try to create an auxiliary a supplementary video. Yeah. So if you are interested, so you can study. Yeah. There is a solution for it. Okay, all right. So we complete part D and module 1 here. Okay, yeah. So we have a little more than 10 minutes. I want to give you a short introduction to our next question. Module 2, part A. So we will learn our next computing problem. So let me give you a brief introduction. Yeah, just do one slide in the next module, part A. Yeah. All right. Module 2. So this module, the title, Analysis of Algorithm Efficiencies and Brute Force Method. The main topic is analysis of algorithm efficiencies. Yeah. The discussion is very abstract. Yeah. Not easy to understand. Yeah. So we need to try very hard to understand algorithm efficiencies. All right. Part A. Problem solving from experience and elimination method. So you can see this elimination method is so important. So we use it everywhere. All right. 8.1, selection sort. So we do our first sorting algorithm, selection sort. So let's look at a question. Our computing problem number 4, sort an array. Given an array, our usual notation like this. Our goal, how to sort it in ascending order. Question is very simple. So I mentioned at the beginning of this class, I mentioned we need to do 3 basic problem types. Now, we did all these 3 types. The first type, search type. Yeah, we did one, linear search. Okay, the first type. The second type we did, selection, find the minimum. That's the selection problem, second type. Okay, the third one, sort here. Okay, we do the sort, the first type in this class. All right, so the type, the reference material, yeah, section 3.1. Yeah. All right, let's do work analysis. Yeah. Here, we need to do problem solving. We need to solve this computing problem. Yeah. Usually, when we solve real-world computing problems, we base on our experience. So we find a solution using our old experience. So here, we need to use our old experience. Although we do not have much experience, but still, some experience is useful here. Yeah. So let's look at what experience we can use in this situation. All right. So first, let's study, let's understand the problem. So let's draw a diagram. We want to understand the problem visually, want to explore, want to discover properties in the current question. Here we do backward thinking, another problem-solving method, backward thinking. So when you start, you assume the array is already sorted. Yeah. So that's the backward thinking. Yeah. So you reach the end of the path, of your solution path. Okay. Yeah. So then you look backward. Okay. Look backward. Yeah. So that's another commonly used method, thinking in problem solving. Yeah. So this time, let's assume the array is sorted. And we want to see what property we can discover in a sorted array. Yeah. Here, in our assumption, we assume distinct elements for convenience. Yeah. Yeah. Many times, we make this assumption. After we find a solution, later we can remove this assumption. Yeah. Because later, after we get a solution, we can easily modify our solution to cover the case with duplicate elements. No. So that's another way that people commonly do. No. At the beginning, assume distinct elements. Later, we can remove that assumption. No. All right? How to connect this problem to the minimum problem? Because here, if you consider our experience, we feel finding the minimum, that's the closest example we can use here. Okay? Yeah. Not polynomial. Finding the evaluate polynomial, that one is not related to this one, right? Polynomial evaluation. And the search, linear search, not related to this one, right? Yeah. So the finding the minimum, that one looks like a little related to this question. So we can borrow some experience from finding the minimum, that example. Yeah. So let's make observation here. Yeah. Yeah. So look at this diagram. Because we already assume this array is sorted in ascending order. A0 less than A1, AN minus 1, right? Yep. Ascending order. Then, if you observe, so pay attention, try to discover some property related to the minimum. Can you get some observation, interesting observation here? Interesting observation, because you want to, use the experience here. So something should be related to the minimum. So when you try to observe some property, can you see something that could be useful regarding the minimum? Regarding the minimum. Okay? Can you see that? Yeah. The first element must be the minimum, right? Yeah, that's the observation. Yeah. If you get whole array sorted, then the first element must be the minimum. Yeah. And you know how to find the minimum, right? You know how to find the minimum. So you don't worry about finding the minimum, okay? Because you know how to do it. Yeah. Yeah. All right. So you know how to find the minimum, and you know minimum must appear as the first element. What can you say? Based on this observation, what can you say about it? Okay? Yeah. Yeah. So what you can say is, if you can find the minimum, then that minimum element must be the first element in the destination array, right? Yep. So you finally sorted that array. So you imagine there is a destination array, okay? The minimum must appear as the first element in the destination array. That's your observation, right? That's your observation, okay? Yeah. So here we need to use a special terminology here, because minimum must appear in the first location in the destination array. So we introduce a concept called in-place concept. So you know the meaning, in place. In its right place. Okay? We put the minimum in its right place, in place. So that means if you apply finding the minimum solution on the given array, you can get the first element in place, right? The first element in place. Think about that. So you make progress. You put one element in place. After that, can you put another element in place? After that, can you put another element in place? One by one in place. Finally, you put all elements in place. Is it sorted? If you put all the elements in place, does it mean the whole array sorted? Yeah. If all the elements are in place, the whole array is sorted, then you're done. But to put the element in place, you only need the solution for finding the minimum. That's all you need. When you apply the solution of finding the minimum, you can put the element in place one by one and put all elements in place. Then you get the whole thing done. That's our idea. That's our first solution. That's our solution. This is a solution. So this solution we call a selection sort. Selection sort. Why selection sort? Why selection sort? Because finding the minimum, we call it selection problem, right? That's the solution of selection problem. Okay? So we use the solution of a selection problem to solve this sorting problem. So we call it selection sort. Okay? All right, so we get a selection sort. So next time we do the analysis of this solution. All right, so that's